Let's learn about static electricity. Static electricity can range from the super spectacular, like lightning, or Van de Graaff generators, to more common phenomena, like getting shocked when you put your finger near the doorknob, or having a balloon near your hair that makes your hair get all staticky. So fundamentally, getting shocked by the doorknob or watching a lightning strike is the same kind of thing, they just differ in amounts. So let's get some basics down. First of all, there's a property of matter called electric charge. As you've learned before, there are two types of electric charge, positive and negative. Electric charge is measured in units called coulombs. Coulombs are a scalar, which means that electric charge, we just care about amounts of them rather than anything about a direction. The smallest amount of charge that an object can have is called an elementary charge, which is represented with a small e. One elementary charge is equal to 1.6 times 10 to the negative 19 coulombs, which is a very, very, very tiny amount of charge. So the electron has a charge of one negative elementary charge. So we use the symbol Q to represent charge. Charge on an electron would equal negative one elementary charge, which is 1.6 times 10 to the negative 19 coulombs, a tiny, tiny, tiny fraction of a coulomb. Protons carry a charge of one positive elementary charge, so we'd write the charge on a proton equals positive 1.6 times 10 to the negative 19 coulombs. So protons and electrons have the same amount of charge, but one of them is positive, the proton, and the electron is negative. Because an electron is a fundamental particle, there are no particles smaller than an electron that are negatively charged. So that means that the least amount of negative charge that I can possibly have is the charge on one electron. So I could say that the charge, the least amount of charge, is just one elementary charge, which is negative 1.6 times 10 to the negative 19 coulombs. Now the next smallest amount of negative charge would be to add another electron, so that would be two elementary charges. So the next smallest amount of charge is two elementary charges, which would be negative 3.2 times 10 to the negative 19 coulombs, or 1.6 times 10 to the negative 19 times 2. So I can't have in between these two charges, this is the next least amount of negative charge I can have. So what would be the next least amount of negative charge? Well, that would be three elementary charges, which would be negative 1.6 times 10 to the negative 19 times 3, which would be negative 4.8 times 10 to the negative 19 coulombs of charge. So electric charge is said to be quantized, meaning it can only have certain values. Q, which represents charge, can only be one elementary charge, or two elementary charges, or three elementary charges, etc., but never 2.63 elementary charges, because you can't have 0.63 of an electron. As I'm sure you've learned before, atoms are composed of protons, which are positively charged, electrons, negatively charged, and neutrons, which are not charged at all. However, only the electrons are free to move through a substance, since the protons are bound together with the neutrons into the nucleus of an atom, and splitting open the nucleus of an atom would require tremendous amounts of energy. But electrons are only loosely bound to the nucleus, therefore removing an electron takes far less energy. So the way objects become charged is either by adding electrons to them, in which case they would be negative, or removing electrons from them, which would make them positive. Positive charges, protons, cannot move. So to make something positive, you would remove electrons rather than adding protons. Some materials allow electrons to pass through them easily. Those materials are called conductors. Materials which inhibit the flow of electrons through them are called insulators. Now, air is actually a very good insulator, but we can see that the insulating properties of air can be broken down, and that's what happens during a lightning discharge. And of course, we have the electricity rule that you probably learned about in middle school, which is that charges exert forces on each other. They interact with each other. Like charges will repel each other. Unlike charges will attract each other. Now, an electroscope is a device that we use to detect the presence of charge. You're going to be using an electroscope as part of an activity. So let me show you what they look like. Now, an electroscope is this box right here, which you have an aluminum ball, which is connected by a rod, goes through the top of the electroscope down here to these two leaves. And these leaves are made out of aluminum. They're very light, and they are just hinged here so that the leaves are free to move back and forth. They can repel each other. So if you were to put charges on the ball, aluminum is a conductor, so the charges can go through the aluminum. The hole into the top of the box has a plastic plug. The plastic is an insulator, which means when charges are present on the ball, they can't go into the outside shell of the box. They have to go down to where the leaves are. So if you bring something charged near an electroscope, you will see the leaves repel, and we're going to see how that works. Now, to see how an electroscope would detect the presence of charge, or why the leaves would move apart if a charge was nearby, consider that the dome has got all these little pluses and minuses on it. The dome actually could be neutral even though all these charges are on it. If the number of positives and negatives are equal, then the total charge here would be 0, even though there's a whole bunch of charges. So this is a neutral ball. Remember, though, that only the electrons can move. Now, what you're going to see here is that over here we have a strip which is charged negative. So you have all these negatives on it. And we're going to bring the negative strip near the electroscope. Here's the electroscope box. Here's the connecting rod, and here's the two leaves. So let's see what happens when we bring the strip near the ball and see how the electrons in the ball respond. Notice that as the negative strip is brought near the ball, the electrons on the ball are repelled away, and they try to run away, and the farthest that they can get is into the leaves. So here they are at the ball, strip is brought near, the electrons are repelled because like charges repel. So the electrons are going to run down as far away as they can get, and how far away they can get is down into the leaves. So now the two leaves have excess electrons and they repel each other. So this electroscope is detecting the presence of charge because the two leaves have become charged from the negative strip being brought near. Now we can also ask, what would have happened if the strip had been positive? Now if the strip had been positive, remember only the electrons can move, a positive strip brought right up to the ball would cause electrons that are already in the leaves to run up to the ball to get as close to this positive strip as they could be, because unlike charges attract. So electrons from the leaves would have run up to the ball to get close to the positive strip, and that would have left the leaves, which are now missing electrons, would have left the leaves positive. So again, the leaves would have repelled each other, and therefore I could detect that this is charged. Now, the leaves, whether the leaves repel or not does not tell me whether whether it's charged positive or negative. It just tells me that there are charges present. Now you're going to be doing a lab using electroscopes, and you're going to be asked to try various things and explain what you see using the 3 rules. So here's the 3 rules. Rule number 1, only the electrons can move because the protons are bound up in a nucleus, so they're not free to move, but only the electrons can move. Second rule is opposite charges attract, like charges repel. And the third rule is that electrons can move through conductors, but they can't go through insulators. And remember also that air is an insulator. So when you come into class, you'll be ready for the electroscope lab.